So now let's proceed to the complete response of a series RLC circuit. Using the same process as the complete response of the parallel RLC circuit, we will get the equations. If you look at these equations, these are the same with the uh, natural response for a series RLC circuit, but for this equation right here, we have a non-zero term or a non-zero constant. But the characteristic equations are still the same. So we have alpha equal to R over 2L. So this is for a series RLC circuit. Then we have omega naught just equivalent to 1 over square root of LC. And same for the complete response for a parallel RLC circuit. So we have, for example, our complete response for VC. We have our forced response plus a natural response. For our current I, we also have a forced response plus a natural response. Where for the natural response, we have three cases, same with the parallel RLC circuit of A, E to the S1T plus BE to the S2T, where S1, S2 equal to negative alpha plus minus square root of alpha squared minus omega naught squared. So this is for the overdamped case where alpha is greater than omega naught. In that case, we have AT e to the ST plus BE to the ST, where S is just equivalent to negative alpha. So for this case, our circuit is critically damped. Alpha is equivalent to omega naught. And our last case, we have A e to the negative alpha t, cosine of WD t plus BE to the negative alpha t, sine of omega d t. We have S is equal to negative alpha plus minus j omega d, where omega d equivalent to square root of omega naught squared minus alpha squared. So for example, we have this circuit. Find IO of 0 plus, VC of 0 plus, DI dt of 0 plus, the roots S1 and S2, and then the expressions I of t and VC of t at t greater than 0. So the switch in the circuit has been in this initial position for a very long time, which means at t less than 0, our circuit is at steady state. We have voltage source, we have this capacitor open, we have resistor in series with short, so from this circuit, so looking at the circuit, our I of 0 minus just equivalent to 0. And then we can solve for VC of 0 minus using VDT. So this is 15K over 15K plus 9K times 80 equal to 50 volts. Now remember, the current in an inductor does not change abruptly, so I of 0 minus is equivalent to I of 0 plus. So same with the voltage across the capacitor. Yeah, VC at 0 minus just equivalent to VC at 0 plus. Now looking at the circuit at T equals to 0 plus, meaning the switch is the other side on this contact B. So we have this circuit. We have VC at 0 plus, uh, I of 0 plus, and we have 100 volts. We have this VR 0 plus, and then we have VL at 0 plus. Okay, VL at this loop, we have VC at 0 plus minus VR of 0 plus minus VL of 0 plus 100 is equal to 0. Now finding for di dt of 0 plus, we can express the voltage across inductor as L di dt of 0 plus. We have the VC of 0 plus minus VR of 0 plus minus L di dt of 0 plus 100. So solving for di dt of 0 plus, we have a value of 10,000 amperes per second. So we'll also get the dvc dt at 0 plus. So we all know we can express I in this circuit as T times dvc dt. So dvc dt at 0 plus is equivalent to I of 0 plus over C is equal to 0. Now we'll analyze the circuit at T greater than 0. Vc of I, we have the value of 5 millihenry and 80 ohms. And we have 2 microfarad, is 100 volts.